Howdy. The point of this video is to look at plastic and elastic deformation on the atomic scale. And specifically, we're going to relate elastic and plastic deformation back to the interatomic force curve that you saw earlier in the semester. Okay, let's start by talking about elastic deformation. Now, you've already seen a stress-strain diagram, so you know that the elastic portion of the curve is typically linear, but more importantly, it's defined by the part with entirely recoverable strain. So that is, if we apply some stress, maybe we're loading the material tensilely, the strain will increase. So I'll follow the stress strain curve up to some point, say here. If I remove that stress, the strain is going to come back to zero. So I'm talking about the elastic portion. The strain is entirely recoverable. There's no permanent deformation after loading the sample up to some arbitrary point. Okay, so what is happening on the atomic scale? Now, in the upper right corner, I'm showing the force versus interatomic distance curve. Attractive forces are on the top half of the curve. Repulsive forces are on the negative half. So if I stretch the material, I increase the interatomic distance. I'm going to larger R's. There's an attractive force that's wanting to draw that, bring that back to equilibrium. If I compress the material, I am putting some compressive loading on a sample. I'm seeing a repulsive force that's forcing those atoms back apart. Now, if you remember before, we mentioned that the elastic modulus is proportional to the slope of the force versus distance curve at the equilibrium distance. Okay, what's going on at the atomic scale? As I start loading the sample, increasing the stress, I'm going to be displacing it from that equilibrium distance. And I'm going to start exerting some attractive force between those atoms. And so you'll see on my representative material over here that those atoms have all stretched a little bit. So if we load it a little bit more, a little bit more, a little bit more, I'm going to continue to stretch those atoms. So as long as I don't go past the yield point, all I've done is I've stretched those atomic bonds. So when I start unloading the material, those bonds are going to want to relax back to their equilibrium position. Let's see that one more time. As I'm loading material, in this case it's under tension, the stress is increasing. The interatomic separation between atoms is increasing in the direction that I'm tensilely loading the sample. And it increases up to that maximum stress that I exert on the sample. And so in this case, the strain is going to be related to that increase in the interatomic separation. As long as I haven't gone past that yield point, when I decrease the stress back to zero, the atoms will all relax back to their equilibrium point. So when a sample is undergoing elastic deformation, you should think about atomic bonds stretching. Okay, what about plastic deformation? So this is the entire rest of the curve where we've exceeded the yield point of the material. Remember, the yield point is defined as the point that serves as the boundary between the elastic and the plastic regions. Okay, plastic deformation, remember, is irreversible. So once I have deformed something plastically, it doesn't go back to that same initial state. So typically we see plastic deformation for larger degrees of stress or strain. Okay, so what happens? Again, initially, a sample undergoes elastic deformation in this relatively small elastic portion of the curve. But as soon as we go past that yield stress, so in this case, the yield stress is somewhere right around here, we start to see a irreversible deformation. So in the case that we're looking at here, this is something that you would see for in a metal, for example. And so that permanent deformation is caused, in this case, by slipping along atomic planes. So let's go back one step. I have increased the stress up to the point where the bonds have stretched just about as much as they want to stretch. The next thing that happens is I start seeing slipping along atomic planes. And that slipping, if you'll notice, led to an increase of the overall elongation. Let's see that one more time. So that slipping increased the overall elongation. So I've increased the strain in the direction that I'm stressing it, that is in a tensile stress manner. And that has happened by slipping along an interatomic plane. And so additional strain could be caused by further slip along that same plane or slip along other nearby planes. But the important part here is that the plastic deformation is accommodated by slip along atomic planes in the case of a crystalline metal. So what happens when I relax this material, when I release the stress? Remember, my bonds are still stretched. So the part of the deformation that is related to the stretching of bonds will be recoverable. But the part of the deformation that is related to slipping along planes is not going to be recoverable. Okay, let's go back and see this one more time. So initially, the material is going to undergo elastic deformation, that is a stretching of bonds. At some point, I'm going to overcome the yield strength of the material, and I'm going to induce some other sort of deformation that is no longer recoverable. So I'm now inducing plastic deformation. In a crystalline metal, the plastic deformation is explained by slipping along crystal planes. And so additional plastic deformation I could get by slipping further along the same plane or by introducing new slip planes in the system. When I remove the stress, I will relax those interatomic bond stretches, but I'm not going to unslip the planes. So that is responsible for the irrecoverable permanent plastic deformation.